Todo mundo me ouve? Ótimo.
Pra que dividir sem raciocinar? Na vida é sempre bom multiplicar. E por A mais B eu quero demonstrar que gosto imensamente de você. Por uma fração infinitesimal, você criou um caso de cálculo integral. E para resolver este problema, eu tenho um teorema banal. Quando dois meios se encontram, desaparece a fração. E se achamos a unidade, está resolvida a questão. Para finalizar, vamos recordar que menos por menos dá mais amor. Se vão as paralelas ao infinito se encontrar, por que demoram tantos corações a se integrar? É que infinitamente, incomensuravelmente, eu estou perdidamente apaixonada por você. Pra que dividir?
Eu vi muita.
Eu não estou falando, né? Eu estou falando e não estou falando. Bom dia no Brasil, a todos e todas.
Luciana, desculpa, antes de você começar, talvez depois pudesse compartilhar, porque eu acho que cortou mas a gente compartilhou lá no comecinho do vídeo, porque cortou as meninas do apoio no fim, na última página. Não sei
Como
por quê.
que cortou?
Eu acho que cortou
Deve ter sido a internet, né?
Não, mas apareceu a fotinha de todo mundo, então tá tudo bem. Pronto.
Não, cortou os nomes. Puxa vida. Tem que ver isso, se aconteceu na outra também. Mas vamos sim, vamos compartilhar daqui a pouquinho. É uma honra para mim hoje. It's a pleasure for me. Good evening, good morning, good night, etc. for everyone. And it's a really pleasure for me today, this plenary talk with Walcy Santos, which is my friend and an excellent researcher, and I'm very emotional about it. And I pass the word to Maria João Rezende to introduce our speaker today.
Hi, good morning, everyone. So Walcy received a graduate and a master's degree in mathematics from the University Federal of Rio de Janeiro, and a PhD at IMPA some years ago. And she currently is a full professor at the Federal University of Rio de Janeiro, and she has experience on differential geometry, working mainly on the mean arc curvature, spatial forms, and plane curves. She was director of the Institute of Mathematics at UFRJ from 2010 and 2018. And she also was part of the board of directors of the Brazilian Mathematics Society from 2017 and 2021. And she was part of the management committee of OBMEP's academic programs when I recently had the pleasure of working and learning with her. So Walcy, thank you so much for accepting the invitation to be a plenary speaker at this Congress. You feel, well, you can speak in English or in Portuguese. I think everyone here understands Portuguese, so welcome.
Thank you, Maria João, and thank you, Luciana, for the nice words. I'm emotional today also. I said to Luciana before that I'm really nervous. I don't know why. Somehow it's the importance of representing women in mathematics and this event that is so necessary. I think that we have to point out that although we are very many, with great equality, we're not so well represented in our community. So it's important all the time to do events that point out these things. I'm going to speak a little in Portuguese just because it's better for me. Celebrar mulheres em matemática é algo que a gente tem que pensar com muita clareza da importância da gente estar sempre tentando quebrar a pirâmide de gênero que a gente tem, onde nós temos uma base relativamente grande de mulheres começando a pesquisa, começando na matemática, e nós temos uma representatividade muito pequena no topo da pirâmide. É claro, muito claro, que a gente tem que virar esse jogo. Não é aceitável que uma comunidade como a nossa não tenha representatividade nos órgãos de fomento, na Academia Brasileira de Ciências, e no resto das representatividades que a gente merece, do tamanho que a comunidade feminina é. Então, a gente só consegue isso, talvez, fazendo, em todo momento, pensando na questão de gênero. Quer em eventos como esse, em que a gente celebra a mulher na matemática, na semana em que a gente comemora o nascimento e partida da nossa medalha Fields, que levou tantos anos para termos uma medalha Fields mulher, que tem uma história de vida impressionante, que nos deixou cedíssimo demais. Mas, por outro lado, a gente tem que estar não só nessa semana celebrando, mas o tempo todo com a questão de gênero na cabeça. É importantíssimo que, em todo momento que a gente estiver vivenciando alguma coisa, a gente pense na representatividade feminina. Estou ficando a chata da questão de gênero, porque eu acho que, em todo momento, a gente deve colocar, principalmente para as meninas que estão começando e pensando numa carreira acadêmica, que a mulher pode chegar onde ela quiser chegar. Nós, mulheres, temos a capacidade de sermos tão boas quanto qualquer pessoa. Nós somos tão capazes quanto podemos chegar aonde a gente quiser chegar. E é muito importante que a gente mostre também as meninas que estão querendo fazer matemática, que mulheres podem ser pessoas de sucesso na carreira. Porque é isso que vai motivá-las a dizer, eu também posso ser uma, eu também posso chegar lá. E a gente pode virar esse jogo. Então, muito obrigada. Por isso que esse evento mexe com o meu coração, muito. Eu já estou emocionada antes de começar a falar. Bom, estamos aqui para falar sobre matemática, sobre um pouco do trabalho de matemática que fiz nos últimos tempos. Esse trabalho tem a ver com artigos em colaboração que eu fiz com Santiago Simanta e Herbert Del Rio. E tem muitas coisas que têm a ver com a tese de doutorado do Thiago Pires, que está por defender a tese na UFRJ sob minha orientação. Então, isso. Obrigado pela atenção. E se a gente quiser, a gente começa agora a falar de matemática. Bom? Qual será o nosso contexto? A gente está querendo estudar uma variedade riemanniana, a Riemann manifold, and we suppose that it is isometrically immersed in an ambient space with a dimension greater or equal to 1. We have the connections, the Riemann connection of M and of M tilde, and they are related because the immersion is isometric. They are related by the second fundamental form, by the equation that is here. And when we have p equal to 1, the dimension is 1, the global, and M has a global normal vector field, you can rewrite this equation in this way, and A is called the shape operator of the immersion. The second fundamental form measure how the surface is curved in the space. A way to measure how it is placed curved in the space. So in order to study alpha, we can study its trace or other combination of it is quadratic linear form. It's a linear form, and we can do linear algebra and to study it. And one thing we can do is the trace of alpha. That is a mean of how curved the surface is in the space. And we call the submanifold totally geodesic if this alpha is identically 0. It's the simplest way we can put on a submanifold in another manifold. It's being no curving at all. I said that it's a simple way, but we have to say that it's not necessary. Do not necessarily have a totally geodesic surface in all ambient spaces. We call the surface submanifold minimum if H is equal to 0. It's the mean is 0. And we are going to study two functionals that we stay here for a while. We are going to study the two functionals that would measure the mean of this, the power of how the surface is curved in the ambient space. As I said, it is alpha is a bilinear form, and there is two simple bilinear forms we can imagine. One is the identically 0, that is related to the total geodesic surface, and another one is the one that are multiply of the metric of the surface. Another way that we can simply create a bilinear form if you have the metric. So we are going the surface that the bilinear form alpha is a multiplier of the metric are called totally umbilic, and we are going to study two functionals that somehow measure how the surface is far from being totally umbilic or totally geodesic in each case. Okay. So the first one is this one. We are going to integrate over M, the functional. I see the immersions M into an ambient space. I calculate the second fundamental form, and I will integrate the norm of the second fundamental form, if it is integrable, of course. And the functional is this one, And I want to study the critical points of this function. We observe that the total geodesic submanifold is obviously a minimizer of this function, because in this case, the norm of the second fundamental form is identically 0, so this is positive. And I can measure how far the submanifold is to be a totally geodesic submanifold of children. Closely related to this functional, there is the Willmore functional that is so many studied by geometers, that is the integral of the norm of the mean curvature. And we can see that this functional measure how far the submanifold is far from being minimal, has h equal to 0. And the third one is a nice combination of this other two, that is the trace of this functional. This is the traceless second fundamental form. Okay, when we do calculations, we see that this expression here is just that. So this functional is just by a combination of the two functionals before. But we see that if M is a total umbilical submanifold, this term is equal to 0, identically 0. So a total umbilical submanifold is clear, a global minimizer for this functional. And this functional, not F here, L, measures how far the submanifold has to be totally umbilical. I was seeing if you think of the ambient space, traditional one, the space of forms, we know that in this space we know totally umbilical, so we know minimal submanifolds, and we know totally geodesic manifolds. But they do not exist at all if the ambient space is more general. For instance, Habas-1 and Eric Tobiana, in the paper Totally Umbilical Surfaces in the Homogeneous Space, they showed that there is no totally umbilical surface, even if I say non-complete, with a piece, in a three-manifold M kappa tau, M3 kappa tau, if tau different from 0 and kappa minus 4 tau squared different from 0. These are the surfaces that describe the possible three spaces, the Poincare conjecture. So they are parts of this series of space. They are so studied in the last decades. So many geometers are studying submanifolds in this space. And they show that in this space, with this special choice of kappa and tau, there is no totally umbilical surface. In particular, since totally geodesic are also totally umbilical, there is no totally geodesic submanifold in this space. So, although they are nicely minimizing for the integral of the second fundamental form or the traceless second fundamental form, the totally geodesic and totally umbilical surface, depending on the ambient space where we are living, there are no examples at all of that surface. So, but when we see this functional, it's clear that it has minimal, just because it is greater than 0 and it has nice qualities. So if you are in a space, in a different space that there is no totally umbilical, for instance, for this functional, or not totally geodesic for that functional, a minimizer, a critical point, or a minimizer for that functional, and the space doesn't have totally geodesic or totally umbilical surface, the global minimizer, or even the critical points, are the surfaces in that hypersurfaces in that space that place the closest properties that a totally geodesic or a totally umbilic surface could play in a space form. That we know that there are many totally geodesic or totally umbilic surface. So the problem is interesting to try to understand the critical points of dysfunctional, even because if you have a surface that there are no totally geodesic or not totally umbilic, that the obvious a global minimizer, who is the surface that has the nice property of being a global minimizer for that functional in that space where we don't have the 0, 0 to be a global minimizer of this functional, because if you know I don't have any totally umbilic, this functional is not 0, so the minimizer will not be 0. So global minimum in an ambient space like that will be someone bigger than 0. So the problem is very much interesting, but hard to understand, even in the case of lower dimension, or we cannot understand it. So even in the ambient space as Euclidean space, spheres, or if I have hyperbolic space, that the space forms that are the natural and easiest, simplest ambient space we can consider. The problem of globally understanding the minimize the critical points and the minimizer of that functionals are not solved at all. So if we cannot understand clear what are the critical points of this functional, what we have done since we are not able to classify everything till now, try to understand what equation the minimizer has to solve, and try to understand some properties when I put some extra condition on my immersion. So I consider to understand the critical points, we are going to do a variation of I have a surface, my immersion. I'm going to variate this immersion in the ambient space, obtain one parameter family of deformation of the immersion name. I call it MT. Okay, and I'm going to ask for a point P on N. Well, I mean, put a coordinate system and M across an interval centering 0, such a way that these coordinates are normal coordinates of the immersion, just to do calculation more easily. The T will be the directional vector of the formation, the variation of the immersion in direction of T. So first of all, we calculate the Euler-Lagrange equation for this functional. In the beginning, for general ambient space, then we specialize in the ambient space. When the ambient space is very general, no hypothesis at all in the ambient space, the equation is that little monster here. Here we have the rich equation of the ambient space. Here is the derivative of the ambient space of the second fundamental form, and so on, so on. Okay. So an isometric immersion, immersive submanifold of M2 that satisfies this Euler-Lagrange equation. The Euler-Lagrange equation of this functional, even only if the normal components of the vector, the normal vector satisfies that this part is identical to 0. So it's not so easy to understand this equation in general, but you can try to understand it better if we put, for instance, the ambient space with constant sectional curvature in order to control these terms. If we put the dimension 1 in order to don't have any p equation, or just one equation. So if you do that in the, for instance, in the space of constant sectional curvature in combination P, if I see an immersion that it's a critical point for this functional, it's a critical point for this functional, if and only if the second fundamental, the mean curvature H satisfies, I call H, the mean curvature H in the H, little h in the direction of a normal vector. This is a function, and this, it has to satisfy this equation. This is more suitable. The equation that involves the mean curvature involves the second fundamental form, and involves the derivative of the vectors in the normal bundle. This is for the first direction, and for the direction of the mean curvature, and the other direction, the equation is this one. Here I have a 0, not the equation involving the Laplacian of a gap of H, and this is the equation for the other directions. For the Willmore functional, that is this one, this is a little more studied in dimension 2 for dimension 1, and also for conjugation P. This problem was more studied, but not in a general space, ambient space. So here we also were able to calculate the variation to try to see the equation that a critical point has to satisfy. And the critical points for this functional must satisfy an equation like that for the direction of the mean curvature. There was another equation that doesn't appear in my slides, that there was the equation in the other directions. Sorry. But I'm going almost all the time work in codimension 1, so not so far. If I ask the ambient space to be Einstein, that is the metric, it's some kind of special. The critical points, we can describe it completely because the terms that appears involving the ambient space are more treatable. So if your hypersurface is an Einstein manifold, Mn is a hypersurface of the Einstein manifold. If it has one in the principal curvature, here we have codimension 1, and these are associated to the principal direction E1 through N, and let nu be the normal field along M. Then M is a critical point of this functional if and only if it has to satisfy this equation. And it's more simple because it disappeared the derivatives of the math, because I suppose the ambient space is Einstein. In the case of the Willmore functional, the critical point has to satisfy this equation. And we note that this equation and this equation, they are essentially, here we have terms that appears here and appear here. And when we combine the second fundamental form with the Willmore functional in order to study the traceless, the functional of the traceless second fundamental form, we have that For this functional, if the variety is the ambient space in Einstein manifold, the critical point of this functional has to satisfy this equation here. That is, it's a little complicated. But if we put that the ambient space has constant sectional curvature, we know all these terms, and the equation becomes this one, and that one is the equation that we are going to work in many cases, in the ambient space being sectional curvature C. So we are going to try to understand the submanifolds that are critical step are critical points of this functional, and then try to understand which of them are stable. We also Thiago, that's my former PhD student. He also calculate the second fundamental form, the second variation of these functionals, and in order to we understand which critical points that could be a minimal or not are in fact stable, that which means that they are really minimal of the functional. In the case that we have a totally umbilical submanifold, we have that all the principal curvatures are equal. That's what can translate that it's totally umbilic. So we put that this in this equation. That is the equation that the submanifold has to satisfy. So this equation is 0, and this equation is also 0. That implies that a total umbilical hypersurface in Einstein manifold has to be with harmonic mean curvature. So if I put in the Einstein manifold that my submanifold is totally umbilic, I have that this equation must be satisfied, and that equation must be satisfied. This is just plugging the fact that the K1 and Kn is equal to K. And this easily implies that the mean curvature has to satisfy the Laplacian of the mean curvature is equal to 0. So the mean curvature in that case, a totally umbilic hypersurface in an Einstein manifold, has to be harmonically mean curvature. We also prove that CFM is compact, totally umbilic in Einstein manifold. Then it has constant mean curvature. So I'm treating of critical points of this functional. But so if you, as you observed before, totally umbilical is critical point of L, and we have that mean curvature is harmonic. So we plug in the this equation, that is 0 is the integration of this equation. This is greater or equal to 0. Since this has to be, this factor has to be 0, so that is the covariant derivative of H is 0. This implies that H is constant. For dimension 2 in this field, the Wilmot's functional was studied a lot, and thanks to Fernando Codar, they solved the parts of the Wilmot conjecture, and also many mathematics contributes to the solution of the Wilmot conjecture that was that if there are tori that could be a critical point of this functional in the sphere. If there are special tori that could be a critical point of the integral of H in this sphere. So if I consider an immersion in the S2 plus P, a critical surface, critical point of the functional L are called also Wilmore surface. So as we before, M2 is a Wilmore surface if and only if it satisfies this equation, where this one is the Laplacian and the normal bundle. We see that any minimal surface is a Wilmore surface. And the question was if there are a tori with constant mean curvature that could be a Wilmore surface. That was the Wilmore conjecture. The class of Wilmore surface turned out to be rather large. The existence of critical points of this functional in the geometric characterization has been object of a number of works. And the solution are both connects to the question to geometric analysis, not only immersions theory. It's geometric analysis that are working hard in this topic. The existence of Wilmore surface that is not constantly curved in ambient states is a very interesting problem. If I have a surface that is a critical point of this functional, but it's not constantly curved. It's not if H equal constant or something like that. Lotto and Mondino show the existence of a critical point of this functional, the tree sphere. Not exactly a tree sphere, but a tree sphere with an absence of perturbations of the round metric. The critical points they construct are, in fact, saddle points of L. So they have index greater than 0. So they are not exact. The index is 4. The number of direction that this functional this manifold has to minimize, not minimize this functional is 4. Up to my knowledge, this is the first existence result for an embedded Wilmore surface saddle type that is not a global minimizer in a compact non-constant curved ambient space. It's not constant curved ambient space because they change a little the round metric of the sphere to construct this example. So it's a very interesting example. They do not find the global minimizer of the functional. That was an interesting problem. They take the sphere, they modify a little the metric of the sphere close to the round sphere, and in this one they study the critical points for the functional L. They do not find the global minimizer, but they find some surface that has index 4. But this functional has a global minimizer. Try to understand which is the global minimizer. In that example, it's also a very nice problem to understand. In order to try to understand also the properties of the critical points, we try to put some extra condition in order to try to classify with this extra condition what could be the critical points of our functional L. So the first thing we can prove, if we have a hypersurface in a space form, that is a critical point of the traceless norm. There are two traceless norm of the second fundamental form functional. If M is a minimal surface, if M has H equal to 0, Then is what we call three-minimal surface. It has the third symmetric function of the curvature also equal to 0. So one thing that you see that the critical points that are the minimal surface has also S3 equal to 0. Well, I will try to understand the reciprocity of this result. What we could be if we put a critical point that has S3 equal to 0. And he asked if it has to be minimal. The minimality it is guaranteed if we put an additional hypothesis on the behavior of the mean curvature in the boundary of the surface. So we get this result. If M is a minimal surface, here is just n plus 1, not r plus 1. Is a critical point of R such that the third symmetric function of the curvature is equal to 0. If the mean curvature is 0 on the boundary of M, then M has to be minimal. So in the critical point that has S3 equal to 0, it inherits the property of being has S3 S1 equal to 0 in the frontal to the interior of the surface. I asked also to Thiago to try to understand the rotational surfaces that could be critical points of this functional, because if you have rotational surfaces, we are putting some symmetry in our critical points and try to understand in the ambient space that we could think in rotational surface, in particular in Rn plus 1, what rotational hypersurface could be a critical point for the functional L. So he begins to understand this problem and try to understand what could figure out what could happen with when we have the curvatures of the surfaces came not in general and values, different values, but in a very at least two principal curvature with multiplicities, or three multiple or three principal curves with multiplicities. So the first case he studied was with two principal curves. Observe that when we have a rotational surface, we have exactly this case, because we have one curvature that describes the curve we are rotating, the other n minus 1 curvatures are also equal. So we have only two possibilities of only two values for the principal curvatures. So first of all, he tried to understand when you have a submanifold of even dimensional in a space form with two principal curvatures, and the multiplicity of these both curvatures are equal. So since here is even, I say it's 2n. So this one has multiplicity n, and this one has multiplicity n. In this case, he was able to prove that if 2n is greater than 4, then m is a critical point of the functional L. It has mean curvature constant, and or it is totally umbilic, or K1 is equal to minus K2. In this case, it has to be a minimal. In this case, when we have a minimal surface, that's the principal curvature comes in pairs, x minus x, y minus y, z minus z. We call this austere. It's a special class of minimal surface, or super minimal. Some authors call it super minimals. They are also studied, and there are clear when we have a minimal angel stare, it's a clear critical point of our functional. And what they prove that if we have this only two principal curvature that has one multiplicity and the other the same multiplicity, the surface or is umbilical or it's austere. It has constant mean curvature, not necessarily minimal. But the second case, we are conclude that the surface are minimal. The case where n is equal to or the surface has dimension 4 and is a critical point of RL if and only if it has constant mean curvature. So the classification comes this way. Under the case m is equal to 1, so the dimension 2 case, m is a critical point of L. Then m has constant mean curvature if and only if it is totally umbilical or a minimal surface. Yeah. If you have a critical point of a compact sequence of this, if you have a compact critical point of the functional L in dimension 3, M2 in dimension 3, with C, the ambient space with curvature greater or equal than 0, then this critical point that is compact has to be a sphere, and it's a classification in low dimension. Still in low dimension, but greater than 2, we have the following results. So in dimension 3, if you have a critical point of L in space form of dimension 4, suppose that it has two principal curvatures that are distinct, K1 and K2, and suppose that K2 has multiplicity 2. One of them that has to be multiplicity 2. So I'm calling K2 the one that has multiplicity 2. Then M has constant mean curvature if and only if M is totally umbilical or K1 is 0 and M is contained is a part of a cylinder. So in this case, we also can classify the critical point that has constant mean curvature. The other case of low dimension is when n is 4 and I have immersion in the space of dimension 5 with two principal curvature, and we are supposing that K2 has multiplicity 3. In this case, M has constant mean curvature if only if it is totally umbilical. As a consequence, we have that there are no rotational minimal hypersurface that are critical points of L in case the space form as dimension n plus 1 if n is greater than 2. So rotational and minimal, no way. So we try to understand the rotational with constant mean curvature. And in this case, in the Euclidean space, we can prove that if it is rotational and it has constant mean curvature, it has to be a sphere, yes, compact and be a sphere. Trying now also to understand the constant mean curvature critical points, rotational critical points. So if you have a hypersurface with constant mean curvature, and it is a critical point of L in the ambient space is the sphere, then M has to be totally umbilical, or I have dimension 2, and M is a minimal hypersurface. Another kind of example, natural example to try to understand the behavior as a critical or not critical point of this functional are the Clifford tori. A Clifford tori it's an immersion of a product of two two spheres in the sphere. So Mn is a sphere as N1 of radius R1 plus N2 of radius R2 into the sphere. I have that the sum of these two dimensions is the dimension n of the variety, and the square of these two radius when we sum has to be one that is the radius of this sphere. Well, the critical tori, we can calculate this critical curvature, K1 and K2. They are this one, this expression. So try to understand the critical tori as a critical point of this functional. We have this one, a minimal critical torus imaginous in this one is a critical point of L diagonally, it is of the form as 2. The dimension here has to be equal, and the radius has to be the square root of 1.5. So the only minimal tori that could be a critical point of our functional is the one that the two spheres has the same dimensions. Okay. I'm going to stop here, just saying that we also prove gap terms for this functional in analogous of a very nice results of Sharon Ducabo and Kobayashi that said that if the second fundamental form of immersion in the sphere is between 0 and some constant, then they classified that the surface has to be the norm of second fundamental form equal to 0, and it's totally geodesic, or it has to be equal to the constant. In the case codimension 1, it has to be a Clifford tori. In the codimension in any codimension, it has to be a Clifford tori or a Veronese hypersurface. We try to understand if this phenomena could occur to the critical point of ours. Since minimal surfaces are critical points for the volume functional, we are trying to understand if such kind of gap terms could hold for the critical points of our functional, and we're able to prove some gap terms analogous to the results of Sharon Ducabo Kobayashi. But I stop here. Oops, at the time. Thanks very much.
Thank you, Walcy. So before the questions, I would like to say that in the YouTube channel, Cecilia Saraiva sent lots of hugs to you, to Professor Walcy, and Nedir do Espírito Santo also is very grateful to being here listening you. So there is any questions to Walcy? You can write on the chat or just turn on the microphone.
Mm-hmm.
Well, I think there are no questions. So thank you, Walcy, very much of being here with us. And well, I think we can.
We are going to make a gift to
I forget.
Okay. Yes.
That is the drawing.
So I would like to thank the audience and the colleagues that that say hello to me. Cecilia, that's what. And then
I think everyone is here. Maybe speak Portuguese. I think.
Ok.
I don't know.
Acho que sim. Acho que podemos
Então
mudar.
a gente pode fazer o sorteio em português.
Se eu soubesse, eu tinha falado em português, ia ser muito mais tranquilo. Mas tudo bem.
Mas a Maria João sugeriu, acho que você estava tão emocionada que não viu. A Maria João
Mas
falou
tem o
que você
YouTube
preferiu.
também, né? A gente não sabe.
Sim,
Então,
Não, pois
é
Tem
verdade,
várias pessoas no
Fernanda.
YouTube.
Eu falei em português a parte emocional da questão do gênero, que era mais importante, eu acho. E depois a matemática conseguiu fluir tudo.
Sim. Foi muito
Exato.
bom, Walcy.
Eu
Gostei
nem
muito.
comentei, porque você mudou do português para o inglês tão naturalmente, eu achei que era para ser assim.
Ok, vamos lá? Quem está aí é a Leslie e a Andressa, né? Vamos fazer o nosso sorteio. O primeiro sorteio vai ser de um livro, um livro ofertado pela Sociedade Brasileira de Matemática Aplicada e Computacional, SBMAC, que é o On Graph Approach to Contextuality and Their Role in Quantum Theory. Ok. The organizers and the speakers, as organizadoras e as palestrantes ou as palestrantes não participam do sorteio, porque a gente, né, ganha outras coisas. Ok.
Calma, mais emoção. Mais emoção.
Calma.
Agora sim,
não,
vai
tem
lá,
mais um.
Andressa. Tem mais um? Ok.
Tem mais um presente.
Sim. Então vamos lá, Andressa. Tem que ter um rufar de tambores, algo, né? Número 2.
2. De Marie Moreno. Manda um e-mail para a gente, avisando, olha, eu ganhei, viu?
E com as informações, né? Com as informações.
Isso, endereço,
nome completo, endereço, tudo. Com CEP, etc.
Número 9.
9, quem era 9?
Deixa eu mostrar o que vai ganhar, criatura.
Mas agora vai a
Fernanda. Eu sei que eu ganhei.
Ela vai
já ganhou, né, Maria Fernanda? Já ganhou.
Não vale tirar, né? Não vale tirar de você. Não, é minha. Mas não sei nem o que é, mas é minha.
Exatamente.
Tá certo.
Então, a Maria Fernanda ganhou o quê? Trabalho,
isso.
Que em geral é isso que a gente ganha, né?
A gente vai te dar trabalho,
muito,
tá certo?
Muito.
Já que você tá com as imagens aí?
Tô. Eu não tinha aberto porque eu achei que você estava fazendo, mas tô.
Mostra aí para nós.
O livro é o kit, né?
Por favor. Isso, exatamente. Mas deixa eu falar, cadê? Foi a Fernanda, né? Peraí. Gente, eu não estou achando vocês. Perdi vocês aqui na minha tela. Achei. Ok.
Mentira que eu perdi também tudo aqui. Não estou achando mais nada. Eu acho que a Fernanda, coitada, não vai ganhar nada.
Não, ela vai ganhar, mas não vai ser o mesmo. Porque no ano passado ela já ganhou um. Que ela foi... Aqui, ó. Vai ser essa aqui. Peraí, que eu já achei aqui. Aqui. Pronto.
Já achou? Então, pronto.
Já achei, já vai.
Então vai.
Ser essa. Tá aparecendo aí?
Tá aparecendo. Adorei.
Bonita.
E o nosso bloquinho, que é esse aqui, ó. O bloquinho sumiu.
Não esquece que o patrocínio dos kits, bolsa, bloquinho,
FAPERJ,
foi
com
dado pela
certeza.
FAPERJ. Valeu, FAPERJ.
E aí a Serrapilheira também vai dar uma força aí para a gente, né, com os envios e tal. Gente, o bloquinho não quer aparecer para vocês, mas depois eu te mostro. Achei ele aqui. Tadam! O Tandam não quer funcionar, hein?
Não.
Olha ele aqui.
Ah.
Finalmente.
Acho que o problema era com a Maria Fernanda. A gente estava...
Ih, Fernanda.
Mas eu vou lá na sua sala e vou pegar, de qualquer jeito. Você queira me dar ou não.
Eu sei onde você fica.
Eu sei onde você fica. Vocês ficam,
Não adianta,
aliás, né?
não adianta
fugir. Não adianta querer fugir, né, gente? Eu vou parar de